स्टार्ट हो गया ना लाइव स्ट्रीम?
Not yet.
Oh, it has started. You should start.
Now it is started.
All
Okay, so
right.
Dipendra,
So
you
shall
can
I
start.
request Dipendra
Yeah,
to
yes,
begin?
yes. Yeah. Go
All
ahead.
right. So it's a great pleasure to have Kartik Prasanna give his second talk of this series. Presumably, he will recall some of the matter which he spoke and which he might need today. So the title of today's talk is Motivic Action for Siegel Modular Forms. Thank you, Kartik, for giving this talk, and please go ahead.
Okay, thank you, Dipendra, for the introduction. Yeah, so this talk will be sort of continuation of last time's talk, but I'll remind people of a few things that I did last time that we actually will need. Okay, so yeah, please stop me if you have questions. I'll try to go slowly. So last time, what we discussed was the Motivic action conjectures for the cohomology of locally symmetric spaces. So I kind of motivated this conjecture and stated it, but let me just recall what the main ingredients are. So there's some group G, some reductive group G, and then we have pi, which is a tempered automorphic representation of GA, cohomological. We assume that it contributes to the cohomology of the trivial local system. So X is the locally associated locally symmetric space. And what we're interested in is the cohomology of X with, say, complex coefficients and the pi isotropic part of it. So the part on which the Hecke operators act by the same Hecke eigenvalues as they act on pi, at least the unramified Hecke operators. Now, what happens is that in general, when you look at something like this is not zero for star in some range. And this range starts from some minimal degree d and goes up till d plus delta for some integer delta. Now, this and so the point of the conjecture is to try to understand, and also one also has the following, that the dimension of hd plus I xc pi is proportional to delta choose I. And so this suggests that there should be an action of some kind of exterior algebra on this total cohomology. And the conjecture with Venkatesh, so this is the paper with Venkatesh in asterisk, makes this sort of conjecture. So what we do there is we identify what is this exterior algebra that is acting on the cohomology, and we make a rationality conjecture. So what is the content of it? For this, we need to remind ourselves something about the Bailenson conjecture, what is called the Bailenson exact sequence. So one of the standard assumptions that we have to make is that there is a motive associated to the adjoint L function. So we'll call this motive ad pi. So this is a weight zero motive. And the key point is to look at the Bailenson conjecture for the adjoint motive. So the Bailenson exact sequence is the following thing that occurs in Bailenson's paper. So I'm going to do this for motives of weight zero. It suffices because the adjoint motive has weight zero. Okay, so the first term is some part of the de Rham cohomology. It's some filtered piece of the de Rham cohomology. The second term is some part of the Betti cohomology. So here you have to take the part in which F infinity and CB act in a certain way. And then the quotient is what is called the Deligne cohomology. So this is some exact sequence of real vector spaces. And the key point or the key observation is that, so let's give this, just for simplicity, let's call this H1D. And this in fact receives a map from something called Motivic cohomology, and this is the regulator map. This is a Q vector space. And the key observation is that the dimension, the real dimension of this H1 Deligne, is the same thing as delta in this case. So if you take the adjoint motive and look at the Beilinson exact sequence and then look at this Deligne cohomology, then the dimension of that is exactly the delta. So in this paper, in this PV paper, what we do is we construct an action of the exterior algebra. So we construct an action of this exterior algebra on this total cohomology. And inside here, via the regulator map, we have the exterior algebra on the Motivic cohomology. And inside here, we have sort of cohomology with Q coefficients. So we're assuming throughout in this that the Hecke eigenvalues of pi live in Q. This is just for simplicity. Otherwise, you could add a number field to this picture. All right. And so the conjecture is this, that this part is the conjecture. The conjecture is that the exterior algebra on the Motivic cohomology actually preserves the Q structure. So the way you should think about this is some kind of a rationality conjecture that relates the cohomology in different degrees. Okay, so let me give an example or remind you of one important example that in fact I discussed in great detail last time, and that actually got us started on this whole thing. The example is overly simplistic because it's only going to be a case where delta equals 1, but even then something interesting happens there. So the motive I want to start with is the following. I start with E, an elliptic curve over K, which is an imaginary quadratic field. And this is associated to some F form F, which is a Bianchi modular form, at least conjecturally. And so the group in this case is the group GL2K. All right. And last time we discussed how we can construct, using Eichler-Shimura maps, we can construct certain periods. And so the point is the following. You start with, this is a weight 2 form. So you start with the space of weight 2 forms. Then there are two, so gamma is the arithmetic group. There are two Eichler-Shimura maps. So one of them goes to H1. Maybe I'll put a P for parabolic. And the other one goes to H2. So this is a situation where the dimension of X, the real dimension of X, is 3. And the total cohomology has, the pi isotopic part of it has dimension 2, but it's split up across 2 degrees, H1 and H2. And there are two Eichler-Shimura maps, which I'll call Eichler-Shimura 1 and Eichler-Shimura 2, and these are related by the Hodge star operator. So this diagram commutes. Now, if you start with a form that is rational, that has a rational QX, you can define a notion of rationality using Q expansions. Then when you apply the first Eichler-Shimura map, you get some period, which I'll call U1F times a rational class. So on the right-hand side, you will have a rational structure by replacing C by Q. And likewise, if you do the same thing, you'll get some other period times the rational class. And again, in this diagram commutes, so you have the hot star operator. So now, if you the way to think about this is the following. Well, first of all, there's the following conjecture, which is due to Cremona and Whitley. So there's going to be two conjectures. The first conjecture is due to Cremona and Whitley, and it's a special case of Deligne's conjecture for some L function. And what it says is that U1F is basically the volume of this elliptic curve. So where omega is in the round differential on E. And the second conjecture, which is basically an unwinding of Bailenson plus using the Cremona-Whitley, is a conjecture about U2 over U1. And so, by the way, so I'll use tilde here for the following: if A over B. So for the moment, instead of to be for the purpose of this talk, I'll just worry about things up to algebraicity and maybe even powers of pi. So I'm not going to be worrying about powers of pi or in this talk. So U2 over U1 is something that we can also compute using Bailenson's conjecture. The point in this whole thing is that the adjoint L value, so L1 pi add, is the product of U1 and U2. On the other hand, this point is S equals 1 is a non-critical point for the adjoint L value, for the adjoint L function. So this is in the realm of Bailenson's conjecture, and you can unwind what a Bailenson's conjecture says. And what it says basically, or what Bailenson will predict, is that there is some Motivic cohomology group, this H1M. And what is it? Practically speaking, the adjoint motive is related to the symmetric square. So it's realized on the self product of E with itself. This is some surface. So E cross E is some surface. And I'll call this, let me call this surface S. And this is, in terms of higher Chow groups, this is the higher Chow group Chow2 S1. So what this, explicitly, you have some collection of curves and functions, Ci, Fi, on the surface with the property. So Fi is a meromorphic function on Ci, and the relation that you need is that the sum of the divisors of Fi is 0 as a zero cycle on S. So you have this collection of curves and functions on them, and on each of them you can take its divisor. This will give you a zero cycle on the curve, which you can think of as a zero cycle on the surface, and then the sum of these things should be 0. So this Chow group is actually given by the group of these things modulo some notion of rational equivalence, which we won't go into. And using these, so what Bailenson will predict is that there is an element alpha, which I'll call alpha, in H1M. In fact, that this rank should be, the rank of this group should be 1. This alpha should be given by some collection of such curves and functions in them. And then finally, this U2 over U1 is the regulator of this element, which is the following. It's the sum over I of the integral over Ci log mod Fi against some form. And what form do we take? We take the following form. You take, I'll call it eta, where eta, restricted to Ci, is P1 upper star omega, which P2 upper star omega bar, plus P1 upper star omega bar, which P2 upper star omega. Okay, so so the point is that when you look at the periods of this Bianchi modular form, conjecturally, you pick up certain very interesting invariants related to E. we don't actually have a way to construct the elliptic curve using the Bianchi modular form, but we can pick up certain things. For example, in principle, we can get the volume. That's part of this Cremona-Whitley conjecture. And then we can also get the regulator of this generator of this higher Chow group. Okay. Right. And so the PV conjecture is really a reflection. So finally, if you go back here, what we see from this is that the Hodge star operator sends a rational class to U2 over U1 times a rational class. And that's why this U2 over U1 is relevant. And what the PV conjecture is really a reflection of this fact of this thing.
Does that triangle commute?
Yes, that triangle commutes.
And
Yeah.
the star is defined over Q, or it's defined over Q?
The star is not defined over Q. No, that's the point. The star will not send a rational class to a rational class. The star is just a Hodge star operator. So it's defined over C, but where it'll send a rational class is to this period U2 over U1 times a rational class. And the U2 over U1 is supposed to be a regulator according to Bailenson. That's the point. Okay. So I guess what I'm saying is that the PV conjecture is really a reflection of this fact that the star, the rationality of star is related to the regulator. So star is rational up to the regulator is rational up to the regulator. But the point is, the thing I want to emphasize is there are actually two conjectures here. One of them is this conjecture that in minimal degree, the period is related to this volume or the faulting's height. And then there is another conjecture which relates what happens in higher degrees to what happens in minimal degree. And that's what the PV conjecture is about. Okay, I'm sorry for the noise. The guy who cuts my lawn decided to show up, and he is, yeah. Hopefully he'll be done. He gets done in a few minutes, so hopefully it shouldn't bother us too much. Okay. All right. So
I mean, just to clarify, I mean, there are two Eichler-Shimura maps, and somehow they are not easily related. That is why U1 and U2 have no simple relationship.
that's right. I mean, there are two. They're related in the sense that there is this commutative diagram, but they don't. But the rational structures are kind of different. So the commutative. So in other words, the star operator doesn't preserve the rational structure. It's only something that's defined with complex coefficients. And so the question is, what does that do to the rational structure? And the point is that it is rational up to this regulator, conjecturally up to this regulator. And so this suggests that there's some relation between the cohomology in minimal degree and the cohomology in higher degrees, which is given by some kind of regulator or Bailenson type element. And that's what the PV conjecture is about. So it's about relating what happens in minimal degree to higher degrees. But the thing I wanted to emphasize is there is also a conjecture in minimal degree, and that's going to play a role later when we talk about the Siegel case. So there are sort of two conjectures floating around here, is the kind of takeaway from here.
Two conjectures
Okay.
because there are two cohomologies.
Well,
One
there's
to
a conjecture
H1,
for
one to
U1
H2.
and then the conjecture for U2 over U1. So that's the point. Okay. So now I want to actually discuss, in this talk, I'm going to discuss a different case, which is the case when X is a Shimura variety. And when you have a Shimura variety, if you start with pi, which is tempered cohomological, then this will only contribute to 1 degree. This only contributes to the middle degree cohomology. So a priori, it doesn't seem like there is something interesting to be said there, but there is if you take forms that are not cohomological. So for example, the simplest example of this is weight 1 forms, GL2Q. So if you start with, so let's just review the case of GL2Q. So if you have some form F of weight K, the cohomological case is when K is bigger than equals 2. So in this case, the form is cohomological, and it contributes to H1 of X with coefficients in some local system, which I'll call Vk. This local system is attached to the representation sim K minus 2 of the group. So that's the case when K is bigger than equals 2. When K is equal to 1, then these forms are not, weight 1 forms don't occur any longer in the cohomology of some local system. And this is why weight 1 forms have been traditionally difficult to study. For example, if you want to construct the Galois representations, these are constructed using congruences. This is the famous paper of Deline and Serre. So the point being that you construct, you use the fact that for higher weight, the forms appear in cohomology, so then you can construct Galois representations. And then for a weight 1 form, essentially the point is by constructing congruences between weight 1 forms and higher weight forms, you construct the Galois representations by constructing them mod some large parts of P. So nevertheless, weight 1 forms contribute to coherent cohomology. And in fact, so if you let omega be the Hodge bundle, then it turns out that if you take a weight 1 form, it'll contribute to both H0 of omega x omega and H1 of x omega. And the pi isotopic components are both one-dimensional. So somehow you see this thing, for if you take a form of higher weight, then the pi isotopic part of the cohomology is two-dimensional. And you see something like that happening with weight 1 forms, except you now have to look at coherent cohomology, and you have to look at 2 different cohomological degrees, and both of them are one-dimensional. So the sum is still 2, but it's spread out across these 2 different degrees. So you might wonder if there is some similar phenomenon similar to what we saw in the non-Shimura variety case, where there's some relation between these the cohomology in different degrees. Okay, so recall that previously we had this Hodge star operator, and really the conjecture was about the rationality properties of this Hodge star operator. That's what happened in that specific case. So what we'd like is some kind of map between H0 and H1. And why does such a map exist? In fact, the easiest way to see that there is such a thing is to look at the higher weight case. So take the case when K is bigger than equals 2. So in this case, we saw already that we are cohomological, and you occur in the cohomology of H1 with coefficients on local system. Now, when you tensor this with C, this has a Hodge structure. I mean, this has a Hodge structure. So when you tensor this with C, this has a Hodge filtration. Then the sub turns out to be H0 of X omega K, and the quotient, so the 2 pieces in the Hodge. Sorry. So the sub is H0 of X omega to K, and the sub is H1 X omega to the 2 minus K. So in other words, these are the 2 pieces in the Hodge structure. So the usual the complex conjugation map will, from Hodge theory, will send H0 of X omega K to H1 of X omega to the 2 minus K. So this is just the C coming from Hodge theory. Now, this map is not rational. So this C is not rational. In what sense? The curve, so of course the C is, so I'll put an XC over here. The curve X is defined over Q. So you can replace C by Q, and you can ask whether C preserves the rational structures, and it's not the case. So in fact, one can check that if you take a rational class omega F and you apply C to it, you get some period times the rational class. And this period is essentially the Peterson inner product of the form F, which we know is the adjoint L value. So you see somehow the adjoint L value coming up here too. Now, this is the case for k bigger than or equals 2. But what happens when k is equal to 1? When k equals 1, you lose this piece. You lose this entirely, but you still retain this. This makes sense. So we can still look at h0 of x omega to the k, h1 of x omega to the 2 minus k. Because k is equal to 1, the k and 2 minus k are the same. And so we now get a map from h0 to h1. Sorry, this is not k. I should remove the k now. This map is basically defined by the same formula as for higher k, and just specialize it to weight 1. And now you can ask, is this map rational or not? And of course, you don't expect it to be, because you see that you should get the adjoint L value propping up. And now the point is exactly the following, that in the GL2 case, when k is bigger than or equals 2, L1 pi add is critical. But when k is equal to 1, then S equals 1, L1 pi add is a non-critical. And so again, you're in the realm of Bailenson conjecture. And because it's you're in a weight, the weight 1 forms correspond to Artin representation, so the adjoint is also an Artin representation. So really, this is related to Stark's conjecture as well. And so what happens here is that when you take C of a rational class, you get some period times a rational class. And this period, now because you're in the realm of Bailenson or Stark's conjecture, should be the log of some unit. So this is a log of a Stark unit. This can be checked in some cases, at least, and Stark checked this kind of thing when he formulated his conjectures, at least in certain cases. And so now this kind of motivates, so now you can ask, is there sort of a more general version of this? Is there a more general conjecture? And this was considered, so the first thing I want to explain is the work of Alex Horawa. And this is his thesis, his Michigan thesis from a couple of years ago. And so Alex studied the case of Hilbert modular forms. So if you look at, for simplicity, let's say that F over Q is a real quadratic field. You can do this with any totally real field. Now, since it's a real quadratic field, Hilbert modular forms will come with 2 weights, K1, K2. And the cohomological case is when both of these weights are bigger than or equals 2. And in this case, you have some surface, a Hilbert modular surface. And again, the cohomological form will contribute to the cohomology of some local system on this Hilbert modular surface. And as before, we have some Hodge filtration. And the Hodge filtration is now has these pieces. So there's the H0. of the sheaf omega k1, k2. And then you get H1 of, maybe I should put this first. Two minus k1, k2. And k1, 2 minus k2. And finally, you have H2 So again, each of these terms is one-dimensional, and so the total contribution is 4 to the cohomology. Now, the most interesting case is and again, you have these complex conjugation maps, but now you have, for each infinite place, you have a complex conjugation map. So these are called partial complex conjugations, which I'll call C1 and C2. And they can be given by some explicit formulas. And they also have a Lie theoretic interpretation. So there's a diagram such as this, which works for which exists for any weights k1 and k2. Now, the most interesting case is when k1 equals k2 equals 1. So again, we have this thing where you lose this, you lose the local system and the cohomology of the local system, but you still retain this diagram where you look at coherent cohomology. And when k1 equals k2 equals 1, these sheaves all become the same. So now we have, and we can't separate these middle terms any longer. So we have a diagram such as this, where when we take the pi isotopic parts, the dimensions are 1, 2, and 1. So again, you see the sort of structure of an exterior algebra that comes up, or at least the dimensions seem to suggest that. And what Horawa does is he exactly formulates the analog of the PV conjecture in this case. So again, the idea is the following. You take the Deligne cohomology, you have to look at the adjoint motive and then look at the Deligne cohomology and take the exterior algebra on the Deligne cohomology. And he constructs an action of this on the total cohomology of X with coefficients in the sheaf. So I should put a C over here because these complex conjugation maps are only defined over C. And then inside here, we have the Motivic cohomology, and the conjecture is very similar, that this preserves the cohomology with Q over Q, the rational structure. Okay. To be very precise, I shouldn't write Q. Maybe it's some number field involved because you have to look at the field of eigenvalues of the weight one form. But let's ignore that for the purposes of this. Now, this seems like some very abstract conjecture, and so but you can explicate this. And when you explicate it, what it's saying is the following. If you start with a weight 1, a form f, which is of weight 1, 1, which is rational, say start with some omega f, you start with a class which is rational and coherent cohomology. When you apply C1 to it or C2 to it, neither of these is going to be rational. So these are classes in H1 of the sheaf, but they're not rational. However, some linear combination of these will be rational. And this linear combination will involve logs of Stark units. So this is explicated in Alex's thesis, and so I won't write it out, but I just want to emphasize that what's happening now is that the middle, the space in the middle is two-dimensional, and these C1 and C2, earlier what happened was that when you look at the case of higher weights, it turns out that C1 and C2, while not rational, are rational up to scalars. But it's no longer going to be the case that C1 and C2 are rational up to scalars. You don't pick up periods in that way. it's a much more complicated phenomenon where you have to take some linear combination of C1 and C2 with some coefficients, and the coefficients involve logs of Stark units. And the Stark unit, there's some Stark unit group in this case, which is rank 2. And in general, if you go to a totally real field of degree D, then the Stark unit group will have rank D, and it's an even more complicated conjecture. All right, so this is what Alex did in his thesis. And now I'll come to the case of Siegel modular forms. All right, so after this, I should mention that there's work of Guggen O. So Guggen O formulated a version of this conjecture for any Shimura variety. But what is missing in general is that, but this is a metrized version.
Kartik, can I
Yes.
just ask a clarification? The
Yes.
space generated by C1 and C2 is two-dimensional.
That's right. That's right. When you apply it to the correct.
It is defined over a number field, or it is not defined over a number field?
No, that's all right. I guess the point is that C1 and C2 don't preserve rationality.
No,
So
individually they
you're right.
don't, but the two-dimensional space perhaps is defined over Q, and maybe that is the content of your saying that the linear combinations involving the Stark log of Stark units make it rational.
That's right. That's right.
So
There's some rational structure, right? So of course there's a rational structure there because the rational structure is just coming from H1 of XQ. So this is
question
some,
was that
yes,
the one-dimensional space under C1 and under C2 are two lines which are
that's
not
right.
rational.
They're not rational. I know multiple of them is rational.
No,
typically.
multiple is rational, but it could happen that the two-dimensional space generated by them is rational.
But what does that mean?
That means that there is a two-dimensional vector space over Q. When you tensor it with C, then it is the same as this space.
But that's more or less by, you're just saying they're linearly independent then somehow?
No. I
no,
mean, you have a vector space over Q, which when you tensor with C, you have these spaces, and you have C1 and C2 belonging to the complex vector space.
Yes.
And the two-dimensional space is complex, but there is a two-dimensional rational space. Suppose the total space was two-dimensional. Then C1 and C2 are already, though they are transcendental objects, they lie in a two-dimensional rational space.
But let me see if I understand what you're saying.
I'm saying that if you have a two-dimensional complex space, which is defined over, which can be also defined over Q, which means that these cohomologies that you have, they have a Q structure, I presume.
Yes, the Q structure just comes from replacing C by Q here, right? In this H1. So there's some natural Q structure.
They have a natural Q structure, and I'm saying that in that natural Q structure, there is a subspace of dimension 2, which when you tensor it with C,
that's right.
Contains the image of C1 and C2.
That's right. That's right.
And maybe that is the content of saying that there is this Motivic cohomology which operates on this.
No, I don't think so. Yeah.
I mean, that seems a bit. All right, please go on. I think I don't want to take up your time.
Yeah, I guess the point is this. So you have some complex vector space and some natural Q structure inside it.
Yes.
Right. And when you apply C1 and C2, you get some lines inside this this complex vector space. Let's say even we take the pi isotopic components, everything is just two-dimensional. We have some two-dimensional thing.
But the fact that these two complex lines are the subspace generated by them is defined over Q is a non-obvious number theoretic statement.
But is that defined over Q? Hold on. What does that mean to Okay, I'm a bit confused what that is saying.
That
If
means
that
that
has
there are rational objects oh, whose complex linear combinations are C1 and C2.
Okay, let's discuss
So
this later,
C1
maybe, because
itself is, as you
yeah,
say, it is not rational. So there is no
yes,
rational object whose multiple is C1.
right,
But one is
right.
saying that the linear
Yeah,
combination of C1, C2, there is a
yes.
linear combination which is rational.
Yeah, but that is already that is clear, I think, because you have this two-dimensional. I think that part is clear. The interesting thing is to say what those
The linear
coefficients are.
combination is, and maybe
Yes,
that's what you said.
yes,
Okay. Good, good.
yes, yeah. And that point is that comes from the logs of these Stark units. That's the content of this. So the content of the conjecture is that basically.
Okay.
It's telling you what those coefficients are. Okay, so there is a version of this conjecture by Gyugen O for any Shimura variety, but it's a metrized version. So really, it's not. So what's missing there is the analog of these complex conjugation maps, these partial complex conjugations. So in other words, he has a conjecture which relates somehow some kind of volumes on the cohomology in different degrees, but there is missing a rationality conjecture because in general one doesn't know how to make the analogs of these complex conjugation maps. So I'm going to actually explain now the GSP4 case, which is this is joint work with Horawa, and you'll see what the issue is. And why this, like what the difficulty in formulating this conjecture is. Nevertheless, we can do something in the GSP4 case. Okay, so now X is a Siegel threefold. So the underlying group is GSP4. And the cohomological, and again, we have now two weights, K1, K2. And the cohomological case is when K1 is bigger than equals K2, bigger than equals 3. So we have some X is some moduli space for abelian surfaces, maybe principally polarized abelian surfaces. And there's a Hodge bundle, omega, which is rank 2. And so a holomorphic form of weight K1, K2 corresponds to a section of the following sheaf, sim K1 minus K2 omega, insert det with K2 omega. And if K2 is bigger than equals 3, then in fact, this is cohomological. So there's some local system, which I'll call L K1, K2. And so now because we're in the threefold, if I take such a form, it will contribute to H3 of X. With coefficients in the sheaf. So the obvious thing to do is to now look at the Hodge structure here and look at what the Hodge filtration is. And now it turns out that you have contributions to H0, H1, H2, and H3. And the sheaves are all different, and these are what the sheaves are. So the first one, so we get H0 of X with coefficients in omega K1, K2. So this is what we started off with. And then H1, so the sheaves change. It's K1, 4 minus K2. And then for H2, it's K2 minus 1, 3 minus K1. And finally, H3. So I should have given myself some space, but 3 minus K1. Oops, sorry, is this right? 3 minus K2. 3 minus K1. And each of these is one-dimensional. So when you take the pi isotropic part, each of these is one-dimensional. Now, the complex conjugation maps that come from Hodge theory will interchange these two parts. So the complex conjugation maps from Hodge theory will go from H0 to H3 and H1 to H2 and conversely. But the interesting case for us now is when you go to a limit of discrete series. So the limit case where it's not cohomological is when K2 is equal to 2. So now we are looking at a form of weight K, 2. And for simplicity, you can even take K equals 2, but let's not do that for a second. So if you take K, 2, you see what happens to the sheaves. So the sheaves become omega K, 2, because K2 is 2. So omega K, 2, omega 1, 3 minus K, and omega 1, 3 minus K. So the first two sheaves become the same, and the last two sheaves become the same. So if you think that there should be some kind of motivic action, the motivic action should go here between these things, between H0 and H1 and H2 and H3. On the other hand, the complex conjugation maps from Hodge theory are useless to define this because those maps go from H0 to H3 and H1 to H2. So there's something. So this is the difficulty in actually defining what the analog of the Hodge star operator is, what the analog of these complex conjugation, the generalized complex conjugation is. So in this work with Horawa, what we do is nevertheless, we identify some map. And I want to explain what that is and then say what the conjecture is. So let us even simplify further. So let's assume that K is equal to 2. In fact, let's make the following assumption. Let's start with some. So the weight K equals 2 is when you have abelian surfaces. So let's start with A, an abelian surface over Q. Of say conductor N. And we'll assume that the endomorphisms of A is just Z. So conjecturally, and there's a conjecture called the Brumer-Kramer conjecture. This should correspond to form F, a Siegel modular form F, of weight 2, 2. And this should have so-called paramodular level. And so I want to explain that there's some kind of nice level structure which gives you submultiplicity 1 phenomenon. So you have some nice theory of new forms. Now, the difficulty or the interesting thing here is that there is an L packet. And this L packet has two elements.
Sorry, did you say that the weight 2, 2 is not a cohomological weight?
It's not cohomological, exactly. 2, 2 is not cohomological. You need K2 to be at least 3 for
where it was cohomological.
That's right. That's right. So abelian surfaces correspond to what are like the analogs of weight 1 forms. And this is why modularity is so much harder to study in this case, because these are not cohomological. So there's an L packet, and the L packet will have two elements. So one of them, so the finite parts will be the same, and at the infinite part, you have two possibilities. You either have the holomorphic discrete series or a generic representation. And what is and the cohomology, of course, so of course these representations, the representations of infinity are not cohomological in the usual sense, but they are coherent they do contribute to coherent cohomology. But the point is that this pi infinity holomorphic, this will contribute to H0 and H3, and the generic will contribute to H1 and H2. And this is what makes life kind of interesting, because somehow when you make this the analog of this complex conjugation map, you have to go from the holomorphic discrete series to the generic discrete series. And it seems really difficult to do at the level of Archimedean representations, because these representations are really quite different. And one doesn't know how to do this. So we kind of do this by fiat. And so let me explain what our definition is of the thing. So what do we do? So what we want to do is we want to make a map. We want some map from H0 of xc omega 2 comma 2 to H1 xc omega 2 comma 2. Some kind of natural map. So, and this map should be related to the Deligne cohomology, which is dimension 1. So what we do is we pick or we identify a kind of natural generator of this Deligne cohomology. I'll call this delta. So delta was previously used in the talk for something else, but now I'll call this delta. So it's a change of notation. And then what we ordain is the following. We say that delta should take a rational class. So this is rational in coherent cohomology here. So it won't send it to something that's rational in coherent cohomology, but we send it to something that's Whittaker rational. So the point is that under our assumptions, these assumptions that we have made, this representation has a global Whittaker model. And so using this thing, there is a way to canonically identify some vector inside here, which is Whittaker rational. And then the way we define this is that we say that delta must act by sending something that's rational in coherent cohomology to something that's rational in this with respect to this Whittaker model. And then the conjecture. So this is just a definition. And the conjecture is that the Motivic cohomology preserves rationality. In other words, if I take a Motivic element, then it'll send a rational class, something that's rational in coherent cohomology to something that's rational in coherent cohomology. So what is the point? So if you can unwind this. So just the same way that all the previous conjectures had some very explicit thing in terms of logs of units or regulators, what this is saying is that if you start with something that's Whittaker rational, this is not going to be rational in coherent cohomology, but if you divide it by some period, it is rational. And what is that period? And this period is related to some regulator. And the regulator comes from Bailenson conjecture. From Bailenson for the adjoint. Okay, so that's sort of the content of the conjecture. So just to summarize again, what we do is we kind of ordain, we say that we find this kind of natural generator of the Deligne cohomology, and then we ordain that should send a class that's rational in coherent cohomology to a Whittaker rational class, and then we conjecture that the Motivic cohomology actually sends a class that's rational to a class that's rational. And the sort of explicit version of this is that if you start with a class that's Whittaker rational, that's in H1, so this is in H1, then it's not going to be rational in coherent cohomology, but it will be so when you divide by some period, and that period should be some regulator which comes from Bailenson. Okay, so that's sort of the explicit content of this conjecture. Okay, so I have a few minutes left, and I just want to say something about two special cases. So the special case is if I start with F, a quadratic field,
So,
And
Kartik, you need this Whittaker model to get the periods, nice periods, so that you can divide.
the period, say it again. What is the question?
No, so you need this model, right? And Whittaker model. So
Yes, we need the model because we want to identify some some form of FW. So we want to make some. We want to identify a specific element, right?
yeah.
In H1, and so the question is how to do that. And so what we're saying is that the contribution to H1 is coming from the generic representation. And so if you have a global Whittaker model, then there is a way to identify a specific vector FW.
So what I'm
That's
saying
what
is that if you have a Whittaker models, can you define the analog of this period? Means like if you have integration over something 0 to infinity.
Yeah, those periods do occur somehow in the proof of all this stuff. So that's right.
Thank you.
Yeah. But the period that is coming up here is not something, is the period that you need there to make it rational is something that's coming from Bailenson. So that's the interesting part here. Okay, so there are two special cases. So, or rather one special case, but you kind of breaks up. So you can take F to be a quadratic field and E over F to be an elliptic curve. And then you can take A to be the restriction of scalars from F to Q of E. So this is a special case of an abelian surface, something that's a restriction of scalars from a quadratic field. And now it turns out there's a dichotomy here. And so the dichotomy is between F real quadratic and F imaginary quadratic. So what happens is when you take the adjoint L value for pi, so in this case, pi is coming from some pi 0, which is on GL to F. If you take the adjoint for pi, it turns out this is a degree 10 L function, and it factors as the product of two L functions. So one of them is the adjoint for the original pi 0, which is degree 6, times the asai L function for pi 0, which is degree 4. And so the dichotomy is the following, that in the real quadratic case, so we have the adjoint of and the asai. So the dichotomy is in the real quadratic case, the adjoint is critical and the asai is non-critical at the point s equals 1. While in the imaginary quadratic case, the adjoint is non-critical and the asai is critical. So there's some interesting dichotomy that happens. And so one of these L values will be critical and the other one will be in the realm of non-critical in the realm of Bailenson, but which one will depend on whether F is real quadratic or imaginary quadratic. So, so I should have said that this conjecture, going back here, we can actually prove this conjecture. So the first theorem is that if we assume Bailenson for the adjoint plus Deligne for the spin L function, you need some twists as well, then this implies the conjecture. So that's the first theorem. The second theorem is the following, that in the real quadratic case,
The Dalin's conjecture is about critical L values.
Critical L values, correct. We have to assume Bailenson for the adjoint and Deligne for the critical, for the spin L function. The second theorem is that in the real quadratic case, we can mostly check this because of work of Ramakrishnan. So Ramakrishnan, so in this case, so Dinakar Ramakrishnan checked part of the Bailenson conjecture for the asai L function. So recall in this case, it's the asai that's non-critical. And so using Ramakrishnan's work, we can more or less check the conjecture. This more or less implies the conjecture. So Ramakrishnan had studied the Bailenson conjecture for the asai L function, where you actually construct explicit elements on a Hilbert modular surface. So so more or less, I have to qualify this, but there's not enough time to explain this in detail. But what I want to say is that more or less one can check this conjecture And then the third case, or the second case here, or the third theorem, is when f is imaginary quadratic. And when f is imaginary quadratic, this should be related to the, now there's also the PV conjecture. And what we essentially check is that, so the theorem is that the Siegel conjecture for pi implies the PV conjecture for pi 0. Okay, so again, I have to qualify this in certain ways. The point is, remember that here there were two conjectures. One of them was the conjecture in minimal degree, and then the other one was the conjecture about relating what happens in minimal degree to higher degrees. And really, the Siegel conjecture is some amalgam of these two conjectures. It's not either of them, but it's some mixture of them. So if you also assume the conjecture in minimal degree, then you get the PV conjecture, or if you assume one, you get the other. So it's some kind of weird mixture of the two conjectures in the imaginary quadratic case. At any rate, what's interesting here is that there seems to be some relation between the Motivic action conjectures for the cohomology of locally symmetric spaces, which are not Hermitian symmetric, to the Motivic action conjectures for coherent cohomology of Shimura varieties. And that's what this last theorem is about. In fact, if you go back to when Galois representations were constructed for pi 0, right? If you start with such a pi 0, and you want to construct the Galois representations, these were constructed by Taylor in his thesis, along with work of who is it? Harris, Taylor, Sudri as well. So the way if you start with a modular form for an imaginary quadratic field, it's hard to construct the Galois representations because the associated symmetric space is not Hermitian symmetric. But what you do is you transfer to GSP4, where you get a weight form that's not cohomological, but that contributes to coherent cohomology. Then you use the analog of the Deligne-Serre construction to construct Galois representations. And then you use that to go back and construct the Galois representations for GL2K. So somehow, even to construct the Galois representation for pi 0, you make this pi. At least this is the original construction of Galois representations. And what we're saying here is that the Motivic actions for pi 0 should be related to the Motivic action for pi. And so there's some relation between the level of these Motivic action conjectures as well. Okay, I think I'm already a few minutes over, so I'll stop here.
All right. Thank you very much, Kartik. Beautiful talk. Very nice. Beautiful. Are there questions?
Yeah, so is this PV conjecture, does it say something about this Brummer-Tillman conjecture?
No, it doesn't. That's totally independent. Yeah. That's a modularity, right? That's completely different.
And you have different lifts, so you have Yoshida lifts and all. So do you have in some particular lift is easier to prove this conjecture, this theorem 2, theorem 3?
Right. So no, it's let me think for a second. Yeah, I think the point, okay, so somehow the Yoshida lifts are endoscopic, right? In this case, yeah. So we have to assume that's not endoscopic. So I should have said that, but when I formulated the conjecture, I formulated for abelian surfaces, where the endomorphism algebra is Q, right? And so those are not endoscopic. So, but in general, we're assuming that I should say this, that pi is not endoscopic.
And
because otherwise it's tricky. It seems tricky to formulate the conjecture in the endoscopic case.
I mean, not only Yoshida lift, Saito Kurokawa and all these lifts.
Yeah, right. So they're all tricky to follow. So we're assuming pi is not special in any of that sort. Yeah.
Thank you.
But it does include the case when it's coming from like this the restriction of scalars from a real or like the functorial transfer from GL2 of a quadratic field is okay, as long as the quadratic field is not Q plus Q.
Meaning these base change lifts are not endoscopic.
They are not endoscopic, yeah. So there must be some conjecture in the endoscopic case, but it seems harder to formulate because now the L packet is larger, so it's not clear exactly how to formulate a conjecture. We don't know how to do this, yeah, or what the correct thing should be.
But perhaps for purposes of abelian surfaces with endomorphism Z, it doesn't happen.
It doesn't happen, no. Those are not endoscopic.
All right. Anything else?
Thank you.
Somebody?
Yeah, so I will have a question. For
Somebody?
theorem, yeah,
Yeah.
theorem 3, Siegel conjecture is implying Prasanna Venkatesh conjecture. And do you have a good suggestion for the Q vector space, the Motivic Q vector space inside the Delin lattice? I mean, Delin cohomology.
Yes, yeah. So no, yeah, what is that? No, the point is that we don't know how to construct it in either case.
Okay.
Yeah. Yeah, I mean, the point is that, one of them will be realized on E cross E, where E is the elliptic curve, and the other one will be realized on A cross A, where A is the restriction of scalars. And so if you knew how to construct the one on E cross E, then you can construct the one on A cross A. But we don't know how to construct either of them.
Okay.
Like nobody knows how to make these motivic elements.
All right. So maybe we end here. I have to also leave. Let's thank Kartik again. Our brilliant talk.
Okay, thank
All
you.
right, Kartik, bye.
Bye-bye, yes.
Devendra, you want to say something?
No, thank you very much for coming
No,
in.
I
this-
mean, many things even I could learn, and I think it has been a wonderful lecture. Great.
Okay, thank you.
Thank you. Bye.
Thank you for
Bye.
sharing the
Thanks,
session.
Kartik, for
Bye. Bye, Kartik. Thanks very
Okay,
much.
see you.
yeah. So we'll close the meeting now. Thanks, Kartik.
Yeah.
We will
Yeah.
meet sometime. And maybe these notes if possible.